Welcome to this coding walkthrough. In this session, we'll tackle the problem of counting trailing zeros in a factorial, known as problem number 172, factorial trailing zeros. This is a fascinating problem that tests your understanding of number theory and efficient algorithms. Let's dive in and explore how to solve it step by step. The problem is to find the number of trailing zeros in the factorial of a given integer n. A trailing zero in a number is produced by a factor of 10, which is the result of multiplying 2 and 5. When calculating a factorial, factors of 2 are much more frequent than factors of 5, so the number of trailing zeros is determined by the number of factors of 5 in the factorial. For example, if we compute the factorial of a number like n equals 5, we need to count how many times 5 appears as a factor in the range from 1 to n. The input for the problem is an integer n, where n ranges from 0 to 10,000, and the output is the count of trailing zeros in n. Let's start with an example to better understand this concept. For n equals 5, the output is 1, because the factorial of 5, which is 120, has exactly one trailing zero. Similarly, for n equals 10, the output is 2, because the factorial of 10, which is 3, 628, 800, ends in 2 trailing zeros. These examples illustrate how the number of trailing zeros grows as n increases, depending on how many factors of 5 are present in the factorial. Now let's look at an edge case to further clarify the problem. When n equals 0, the factorial of 0 is defined as 1, which has no trailing zeros. Therefore, the output in this case is 0. This demonstrates that even though we're working with factorials, the problem doesn't require us to directly compute the factorial itself, especially for larger values of n. Instead, we can simplify the problem by focusing solely on counting the factors of 5 in the range from 1 to n, including higher powers of 5 like 25 or 125, which contribute additional factors of 5. This insight is key to solving the problem efficiently. To solve the problem efficiently, the approach is to repeatedly divide n by 5 and sum up the quotients. Each division by 5 counts how many multiples of 5 are present, which contribute factors of 5. For larger powers of 5, such as 25, 125, or higher, we continue dividing until the result of the division is less than 1. This ensures that all factors of 5, including those from higher powers, are accounted for in the total count, allowing us to determine the number of trailing zeros in n, without ever needing to compute the factorial explicitly. To start solving the problem of counting trailing zeros in a factorial, one straightforward approach is the brute force method. The intuition here is to calculate the factorial of n, which is the product of all integers from 1 to n, and then examine the resulting number to count how many trailing zeros it has. Since trailing zeros are formed by factors of 10, which in turn come from pairs of 2 and 5, this approach involves computing the entire factorial, then either converting it to a string or using modulo operations to determine how many trailing zeros exist. While this method is easy to implement and directly solves the problem, it has significant downsides. Factorials grow extremely quickly, and for even moderately large values of n, such as 100, the result becomes so large that it's impractical to compute or store. Additionally, the time complexity of O(n) for calculating the factorial and the space required to handle large numbers make this approach inefficient for larger inputs. These trade-offs make it clear that we need a more efficient solution. Recognizing the inefficiency of brute force leads us to a more optimized mathematical approach. The key insight here is that trailing zeros in a factorial are caused by factors of 10, and factors of 10 are produced by multiplying 2 and 5. However, in any factorial, there are always more factors of 2 than factors of 5. This means that the number of trailing zeros is determined solely by the count of factors of 5 in the numbers from 1 to n. To calculate this, we can count how many numbers between 1 and n are divisible by 5, then by 25, then by 125, and so on. Each higher power of 5 contributes additional factors. For instance, in the case of 25, it contributes an extra factor of 5 for every multiple. This insight allows us to avoid computing the factorial entirely. Instead, we initialize a variable to track the count of factors of 5, divide n by 5 and add the quotient to this count, and repeat this process for each higher power of 5 until a quotient of 0 is reached. The result is a time complexity of O log base 5 of n, since we are repeatedly dividing n by 5, and a space complexity of O 1, as we only use a few variables. This approach is significantly more efficient and avoids the computational challenges of the brute force method. Given the inefficiencies of the brute force method, the optimized mathematical approach stands out as the best choice for solving this problem. By focusing on the core observation that trailing zeros depend only on the factors of 5 and n, this method avoids computing the factorial altogether and achieves a logarithmic time complexity. It is both elegant and highly efficient, making it scalable for very large values of n. Comparing the two approaches, the brute force method is infeasible for large n due to the rapid growth of factorials, while the optimized approach directly targets the problem and avoids unnecessary computations. Additionally, there are no other practical methods that solve this problem as effectively, as this approach minimizes both time and space usage while addressing the core issue. It also handles edge cases, such as n being 0 or very small, seamlessly without requiring special adjustments. In conclusion, the optimized mathematical approach is the most efficient, elegant, and practical solution to this problem, balancing simplicity with performance and scalability. The problem asks us to determine the number of trailing zeros in the factorial of a given number, and trailing zeros in a number are produced by factors of 10, and since 10 is the product of 2 and 5, the key is to count how many factors of 5 are present in the factorial. This is because there are always more factors of 2 than 5 in any factorial. Instead of calculating the factorial, which grows very large very quickly, we can focus solely on counting these factors of 5 efficiently. The algorithm starts by initializing a counter variable to 0. This counter will keep track of the total number of factors of 5 we encounter. Then, we repeatedly divide n by 5, adding the result of each division to the counter. This process captures contributions from numbers like 5, 25, 125, and so on, which introduce additional factors of 5 into the factorial. The loop continues until the result of dividing n by 5 becomes 0, at which point there are no more factors of 5 to count. Once the repeated division by 5 reduces the value of n to 0, the loop terminates. At this stage, the counter variable contains the total number of trailing zeros in n. This count is then returned as the final answer. To understand this better, let's go through an example. Suppose we want to find the number of trailing zeros in 100. We start by initializing our count to 0. First, divide 100 by 5 to get 20. Add this to the count, making it 20. Next, divide 20 by 5 to get 4, and add this to the count, bringing it to 24. Finally, divide 4 by 5, which gives 0, so the loop stops. The total count is 24, meaning 100 has 24 trailing zeros. This approach avoids computing the factorial directly, which would be infeasible for large numbers like 100, as its size grows astronomically. Instead, we efficiently count only the factors of 5 that contribute to trailing zeros. This method also stands out for its logarithmic complexity. Since each division reduces n by a factor of 5, the loop runs approximately log base 5 of n times. This makes the algorithm highly efficient even for very large values of n. Additionally, it handles edge cases seamlessly. For example, if n is 0, the result is simply 0 because 0 equals 1, which has no trailing zeros. For small values of n, such as numbers between 1 and 4, the count remains 0 because there are no factors of 5 in these cases. What's more, this approach requires minimal resources. A single integer variable is sufficient to maintain the count, so it operates in constant space. There's no need for arrays or additional data structures since we're not storing intermediate results. The simplicity of this solution underscores its efficiency and practicality for this problem. The algorithm further benefits from optimizations that make it both straightforward and fast. The loop exits as soon as n divided by 5 becomes 0, ensuring we don't perform unnecessary iterations. Instead of iterating through every number up to n, we directly calculate the contributions from powers of 5, skipping over numbers that don't add new factors of 5. This targeted approach reduces computational overhead significantly. In terms of complexity, the time complexity is O log n, due to the repeated division by 5, and the space complexity is O 1, since only one variable is used. To summarize the steps in pseudocode, initialize a counter to 0, repeatedly divide n by 5 while adding the result to the counter, and finally return the counter once the loop ends. This concise implementation ensures both clarity and efficiency, making it ideal for solving the problem of counting trailing zeros in factorials. It's also important to address specific edge cases to ensure the algorithm works in all scenarios. For instance, when n equals 0, the output is 0 because 0 equals 1, which has no trailing zeros. For small values of n, such as numbers between 1 and 4, no factors of 5 exist, so the count remains 0. On the other hand, for very large values of n, the algorithm remains efficient due to its logarithmic time complexity. This robustness, combined with its simplicity, makes the algorithm a reliable solution for the problem. By focusing only on factors of 5 and leveraging efficient arithmetic operations, we avoid unnecessary computations, ensuring the method is not only accurate but also optimized for performance in all cases. This implementation efficiently calculates the number of trailing zeros in the factorial of a given number n by counting the factors of 5. Trailing zeros are formed when factors of 10 appear in the factorial, and since each 10 is the product of 2 and 5, the limiting factor is the number of 5s in the factorization of the numbers from 1 to n. The trailing zeros function starts by initializing a variable count to store the total number of factors of 5. Then, it enters a loop where it repeatedly divides n by 5, using integer division, and adds the result to count. This process works because every multiple of 5 contributes at least one factor of 5, every multiple of 25 contributes an additional factor of 5, and so on. By summing these contributions, we accurately count all the factors of 5 in n. For example, if n equals 25, the first division adds 25//5 equals 5 to count, accounting for the numbers 5, 10, 15, 20, and 25. The second division adds 5//5 equals 1 for the extra factor of 5 and 25. Thus, the total count is 6, which is the number of trailing zeros in 25. The loop terminates when n becomes 0, which ensures that all factors of 5 have been counted. This approach runs in O log n time, as the input n is divided by 5 in each iteration, making it highly efficient even for large inputs. The function then returns the final count of trailing zeros. This is the Java implementation of the LeetCode problem number 172, factorial trailing zeros. The logic is equivalent to the provided Python implementation. It calculates the number of trailing zeros in the factorial of a given number n. In Java, we use explicit type declarations for variables such as int. The method iteratively divides n by 5, accumulating the count of multiples of 5, which contribute to trailing zeros in the factorial. The solution efficiently handles large inputs through this logarithmic approach. The problem is all about finding the number of trailing zeros in the factorial of a given integer n. Trailing zeros happen because of factors of 10, and since 10 is the product of 2 and 5, the key is to count how many factors of 5 are in the factorial. This works because for every factor of 5, there's already a corresponding factor of 2 to pair it with. To solve this, we repeatedly divide n by 5 and add up the results, which gives us the total number of factors of 5 in the range from 1 to n. For example, if n equals 5, we start with n equal to 5 and count at each step. First, dividing 5 by 5 gives us 1, so we add that to our count, which becomes 1. Then we update n to 1 and repeat the process. This time, dividing 1 by 5 gives 0, so we stop. The total count is 1, meaning there's exactly one trailing 0 in 5 factorial, which makes sense because 5 factorial equals 120, and 120 has one trailing 0. Now let's consider when n equals 10. Initially, n is 10, and the count starts at 0. Dividing 10 by 5 gives 2, so we add 2 to our count, which now becomes 2. Then we update n to 2 and continue. Dividing 2 by 5 gives 0, so we stop, with a final count of 2. This tells us that there are 2 trailing zeros in 10 factorial. If we compute 10 factorial, which equals 3,628,800, we can confirm that the number indeed ends with 2 trailing zeros. This result happens because the range from 1 to 10 includes 2 multiples of 5, 5 and 10, each contributing a factor of 5. For n equal to 25, the process is similar but involves more iterations. Starting with n is 25 and a count of 0, we divide 25 by 5, which gives 5. Adding 5 to the count makes it 5, and we update n to 5. On the next iteration, dividing 5 by 5 gives 1. Adding 1 to the count brings it to 6, and we update n to 1. Finally, dividing 1 by 5 gives 0, so the loop ends. The final count is 6, meaning there are 6 trailing zeros in 25 factorial. This happens because numbers like 5, 10, 15, and 20 each contribute one factor of 5, while 25 contributes two factors of 5 due to it being 5 squared. This extra contribution from higher powers of 5 is why we need multiple iterations to capture all the factors. The key idea behind this approach is that each division by 5 counts all the factors of 5 contributed by numbers in the range from 1 to n. Additionally, higher powers of 5, such as 25 or 125, contribute extra factors, which is why we keep dividing until n becomes 0. This ensures we account for all factors of 5 efficiently. The time complexity of this solution is logarithmic with base 5, or O, log base 5 of n, because we're repeatedly dividing n by 5. This makes the solution highly efficient, especially compared to computing the full factorial, which would be infeasible for large values of n, as factorials grow extremely quickly. The time complexity of this problem is O, log n, and we can understand this by examining the loop in the code. Each iteration of the loop divides the input, n, by 5. This division reduces n by a factor of 5 with every step. The process continues until n becomes 0. Mathematically, the number of iterations corresponds to log base 5 of n, or log underscore 5, n. Since logarithms of different bases are related by a constant factor, this simplifies to O, log n, for the time complexity. For space complexity, the algorithm is very efficient at O, 1. This is because the code only uses a fixed amount of memory, regardless of the size of the input. The variables count and n are simple scalar values, and no additional data structures like arrays or recursion are required. This ensures that the memory usage remains constant, regardless of how large n gets. Now, let's analyze the best, average, and worst cases. The best case occurs when n is very small, such as 0 or 4. In these cases, the loop doesn't execute at all, and the function completes in constant time, O, 1. For the average and worst cases, as n grows larger, the number of iterations depends on log underscore 5, n, leading to a time complexity of O, log n. Interestingly, the worst case behavior here is the same as the average case behavior. Comparing this to a brute force or naive approach, we see a significant improvement. With a brute force method, we would have to compute the full factorial of n and then count trailing zeros. This would require a time complexity of O, n, to compute the factorial and additional space of O, n, to store the result, which becomes infeasible for large values of n due to the sheer size of factorials. In contrast, our optimized approach avoids this entirely by focusing only on counting the factors of 5 and n, which directly determine the trailing zeros. This results in a time complexity of O, log n, and a space complexity of O, 1, making it far more efficient. To understand why the time complexity is O, log n, we can look at the mathematical reasoning behind it. The number of trailing zeros in n is determined by the number of factors of 5 in the numbers from 1 to n. Each division by 5 identifies the multiples of 5, then multiples of 25, 125, and so on. This process continues until n becomes 0. The total number of iterations is approximately log underscore 5, n. Since logarithms of different bases differ only by a constant factor, we can convert log underscore 5, n, into log underscore 10, n, divided by log underscore 10, 5, which simplifies the time complexity to O, log n. This mathematical insight highlights why the optimized solution is so efficient. By avoiding the computational and memory overhead of explicitly calculating factorials, this approach is not only faster but also scalable to very large values of n, making it a highly effective solution. When tackling this problem, there are a few common mistakes to watch out for. First, some candidates misunderstand the requirements and attempt to compute the entire factorial explicitly. This is inefficient and can lead to overflow errors for large inputs. Instead, focus on counting the factors of 5 in the factorial's decomposition, as each factor of 5 pairs with a factor of 2 to form a trailing zero. Another mistake is incorrectly handling numbers like 25, 125, or higher powers of 5. These contribute more than one factor of 5, such as 25 contributing 2, and forgetting this can lead to undercounting the trailing zeros. Additionally, using floating point arithmetic to solve this problem is unnecessary and prone to precision errors. Integer-based approaches are simpler and more reliable. Finally, inefficient solutions, like iterating through all numbers from 1 to n, will time out for large inputs. Instead, the optimal method is to repeatedly divide n by 5 to count factors of 5 directly, which ensures logarithmic complexity. Another important consideration is edge cases. For example, when n equals 0, the output should be 0 because 0 factorial equals 1, which has no trailing zeros. These edge cases are easy to overlook but crucial for a correct implementation. Now, let's delve into insights that can help during interviews. A key insight is that trailing zeros come from factors of 10, which are formed by multiplying 2 and 5. Since factorial decompositions always have more factors of 2 than 5, the problem simplifies to counting the factors of 5 and numbers from 1 to n. Interviewers typically expect you to use the logarithmic approach, which involves repeatedly dividing n by 5, demonstrating both mathematical reasoning and computational efficiency. It's also important to communicate edge cases explicitly during an interview, as it shows thoroughness and attention to detail. This problem is often used to test analytical thinking and the ability to simplify computations through mathematical properties rather than brute force. This problem is closely related to some other common algorithmic challenges. For example, LeetCode 1363, largest multiple of 3, involves counting specific factors for divisibility, while LeetCode 793, pre-image size of factorial zeros function, is essentially the inverse problem of finding the value of n for a given number of trailing zeros. Another related problem is LeetCode 343, integer break, which involves optimization concepts. Understanding these related problems can provide additional context and help you recognize patterns across different challenges. Now, let's touch on alternative approaches. One approach is to explicitly compute the factorial of n and then count the trailing zeros by converting it to a string and counting the trailing zeros. However, this brute force method is highly inefficient for large n due to the rapid growth of factorials and potential overflow issues, making it impractical for most scenarios. Another alternative is a digit-based counting approach, where you directly count the number of 5s in numbers from 1 to n. While computationally feasible, this method is less intuitive and more complex to implement compared to the logarithmic method. A third option is recursive counting of factors of 5. This involves implementing a recursive function that divides n by 5 repeatedly to count the factors of 5. While this approach can be elegant, it risks stack overflow issues for very large inputs unless tail recursion is optimized. In terms of complexity, the optimal approach of logarithmic counting achieves a time complexity of O log n and a constant space complexity of O 1, making it the most efficient solution. In contrast, the brute force approach has a time complexity of O n, which is significantly less efficient. For best results, always aim for the logarithmic solution, as it balances simplicity, efficiency, and scalability. Great job making it to the end. In summary, we explored how to count trailing zeros in a factorial using an optimized, logarithmic approach. This problem highlights the power of mathematical insights in algorithm design. Thank you for watching, and be sure to like, subscribe, and share for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!